we actually have a simulator now, right? Everything is working. We've got high accuracy. I set the starting point, and it worked to simulate the motion of the pendulum. What we could do is make this a little fancier, say for future project use. What we could do is turn off this plot thing, and instead I'm going to save this. Actually, sorry, let me undo that. Save that version. And we'll save a new version as 8.4. And what we can do is animate this without too much trouble at all, because we have the time values. So again, what do we have? We have a bunch of time values from 0 to 10. We have a bunch of position and velocity values. We could animate the motion by looping over these things. So we're going to loop over the rows. So I is going to equal to 1 to the length of my t vector. So for every t value I have, I'm going to grab the time, and I'm going to plot the x and y that goes with that. Then I go to the next time, plot the x and y that goes with that. So that should be a freeze frame motion of this pendulum swinging back and forth. And what we can do there is just plot the W1. Oh, wait, careful here. The rows go with time or with the variable? The rows of W. Time. So we want the ith row, and if I want the x coordinate, which column is it in? Column 1. If I want the ith row but the y coordinate, which column is that in altogether? 3. Exactly. No j. And we'll put a dot there. We can make that a little fancier as well by actually adding a line. So we can do a hold on here. Hold on. And we can plot a line back to the origin. So wi, comma 1. Sorry, we're going to draw a line. Oh, God, this is just going to be horrible. This is where when you start reusing things, it's nice to give it a name. So let's call that our current x coordinate, and call the other thing our current y coordinate. That'll make this look a lot nicer. So we're going to put a dot at x, y, our current x and y, and then we're going to plot a line from 0 to x and from 0 to y, like so. All right. So that should draw both the rod and the mass, and let's see what it looks like, and we can always adjust. Funky. It's pretty. Not quite what I had in mind. There's a couple of things that, if you've done the animation, should spring to mind. How can I, A, animate this, because it's not animated, and B, fix this fan effect that we're getting? Use get frame, exactly, or draw now, or any of the above. So we need to show it. I like draw now just because it's a lighter weight option, but you could also use get frame. And if we do that, then we start seeing the animation happening. So OK, we're in the right ballpark, but it's a little awkward looking. How could we? It just doesn't. Control C is your friend here. You want to stop it. What else could we do to make that look a little better? CLF, right. At the beginning, we want to have a clear frame every time. If we had a CLF to the top, it'll clear the frame every time. And now this is a little horrible for other reasons, but it only shows one line at a time. How can we fix the fact that it's kind of giving me epilepsy by looking at it? Yeah. X lim and Y lim, exactly. If we say I want to show from -2, let's go from -2 to 2 in x, and the y lim from -2 to 2 in y, that will give us a common viewing window. And hello, there we go. All right. So that is using the output of the simulation in a different kind of way. Just go back to the notes of the code here. So let me just run that one more time. I'm going to ask you, does this look, actually I'm going to do one last thing, which is put axis equal on here so everything actually is the same size. I'll run it again. Does it seem totally realistic, smooth? Something seems off, right? Like it seems to hang there longer than it should, things like that. Let's take a look at what we're plotting with. We're plotting with the W values, but the T values are, we're incrementing one T value every time. In an animation, I would like that time interval to be the same every time. Are we actually getting the same time interval between time steps here, though? No, right, that's a problem. It's a good thing, don't get me wrong. If we just cared about the plot, we wouldn't care. But because we're trying to animate this with even time steps, this is an issue. And the reason we have non-even time steps is because this solver, like the solvers or the integrators we saw last week, adapts and uses, you can imagine, it's hard to predict exactly the motion near the end, so it uses really, really small time steps. And then during the big swing parts, things are going pretty smoothly. It uses longer time intervals. And so what we get in the output is small time intervals sometimes, and then longer time intervals elsewhere. Who here is in the roller coaster project? Fantastic. OK, pay attention to this, because it's going to play a role in yours, too. So the simulator is ODE 45. So we're going to look this up in our help menu and see if we can tweak this. What we're worried about is the time. So I want you to focus on this part here. So the time span that we gave it was 0 to 10. We just said simulate from 0 to 10 seconds. However, there's more we can do. To obtain the solutions at specific times, i.e., let's say every 10th of a second, you can get MATLAB to do that for you. You don't give it 0 to 10, though. You give it a vector of 0, 0.1, 0.2, blah, 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 out to 10. So it's a tweak like this tiny, but it makes all the difference in the world when it comes to this animation phase, which is, where's our simulator? This is the thing that does all the solving. Instead of 0 to t end, let's say 0 by 0.1s of a second to 10. I'm just going to comment out the animation for 1 second while we do this. Just remember, these t values that happened with the default settings, when we run it again and I look at the t values, now they're spaced every 10th of a second. And so the matching w values that go with those would be spaced every 10th of a second. They're the matching positions and velocities, so they had the same time intervals. So all we did was change the time span and how we represented it. We can now bring this all back in and simulate it again. Now it's a little spazzy, but it certainly seems more realistic. Let's make the time span a little shorter, because apparently things are happening pretty quick. Let's say 0.02. And run that instead. Now that looks like the kind of motion we'd expect. Smooth, slows down where it's supposed to slow down, speeds up where it's supposed to speed up, because now our positions are actually in line with even time steps. So each frame represents the same amount of time passing. The swinging back and forth is a bit awkward. I haven't found a nice way to do that. I think is the axis equal that's causing that? Let me try one thing here. Get that out. I'll put the axis equal first. Honestly, this is a gravy kind of thing. Oh, that's better. There we go. So order of the various limits and equal axes and stuff like that does have an impact. But this is awesome, I think. I think it's slowing down a little bit, mostly because my computer starts lagging at some of these phases. But each interval would actually be the same time span now. OK. When you're modeling, for the roller coaster folks, the motion of your cart, you're going to have to do the same kind of tweak when you solve your differential equation for the motion of the car on the track. All right, now I'm going to ask you a question. We're going to tweak this one more time. We'll change the initial starting point, which is all the way up here. W0 is our initial starting position, velocity, position, velocity. So what we're going to do is put this thing over above the axis of rotation. And when we do that, we get that kind of rotation, which is kind of nice. If I wanted to give it a starting kick, where are we in the picture? We are in the picture currently at -1. Wrong thing. We're at -1, 1. That's where our ball is relative to here. If I wanted to give it a velocity, what direction would I put the velocity in? 0, -1? OK, let's figure that out. So if I did that, what we'd be saying is x prime equals 0 and y prime equals -1, right? Because that'd be a down vector. We can put that in our initial values by remembering this is W2 and this is W4. So if we try that out, our W2 now is not 0. It's not it's 0 again. Sorry, it is 0. And this is -1. And I'm going to do that again. something, that's a yo-yo. That's not a pendulum. That wasn't right. Why was that not right?
Not tangential.
It's not tangential, exactly. If that was my pendulum with a rod, it has to move perpendicular. Motion is always going to be, the acceleration velocity, sorry, the velocity always has to be perpendicular to your position. So we need to ratchet that green vector out to be perpendicular. Then we will actually get a consistent length. So it's kind of fun to not do that because you get that effect we just saw. So it has to be perpendicular. What x part would make that perpendicular? -2. This is 45 degrees here. So this would be 90 degrees at 45. X prime would equal -1. Yeah, just -1, -1 would do just fine. And we can try that out here. -1. And now it's going to look like a pendulum again. Same length all the time, and so on. And notice it goes a bit further than it did before. So what we can also do is experiment. Stop that for a second. Control C again is your friend. We can experiment and actually boost up that velocity. Let's call it V0. I'll make it 3 or something. And then make this minus V0 and V0 minus V0 here. So just we change one number, and there we go. And now we can get the thing spinning around forever. We don't have friction in this model yet. But we can tweak all of those parameters. We can't make it go away. But we can tweak all those parameters and simulate whatever kind of motion makes sense for what you're trying to achieve.